Hello again, folks. Today we're going to be covering section 5.1, quadratic functions. Here's a quick view of the calendar. Kind of do this in my own thing too, you know. This video is for Wednesday, June 1st. So we'll be covering 5.1. If I didn't have that reminder, I might not know what day it is, believe it or not. Anyhow, the packet that I have for you today is this overview. This is not anything but for the sake of clarity, I hope. Right? To this point in the conversation, including today, we'll have covered this material. All right? And what's forthcoming is what is known as the transcendental functions. I purposely left this blank because it can be overwhelming this side alone. So anyhow, I'm going to explain this. And I wanted you to have some inkling as to where we are and where we're going. All right. Now, the topic of conversation today, you'll notice that we have the quadratics that we're going to be discussing. There's different forms of it, and they have different benefits, especially these two. All right. You're really only responsible for these two, but this exists. And when we get into rational functions, I feel like having some awareness of this would have been to somebody's benefit. So I included that. This is a list of features of quadratic functions, things to look for immediately, and pretty much this order. The only thing I neglected to do, and I'm going to annotate, is maybe put a number here and here down the list to sort of be the procedure, if you will. And then always some graph paper. Could print out a couple of those. And this is just an overview of how you could use a calculator. I think that's it for this packet, yes. Okay, so if you're following along, do print this and I'll start to talk about it. Hopefully the domestic disturbances outside will pass us by. Hopefully it's not something serious. Okay, so computer here. Nope, don't want that. Alright. I have to leave the window open because it's rather hot today. I'd rather not keel over on camera at least. Alright, I think I'm gonna have to close the shade anyway. See if this requires movement. There we go. That looks reasonable, right? I think so. Yeah, it's pretty clear. Good. All right. As I said, pre-calculus class consists of basically these two ideas. All right, algebraic functions and transcendental functions. Transcendental functions, you probably have some awareness of. If you've ever seen exponential equations, or if you've ever played around with your calculator, even a scientific calculator would have trig functions, like sine, cosine, and tangent. That is forthcoming. All right, where we are is here, and this is where we've been. I tried to leave in some key features here for the sake of comparison. So. Usually what we begin with in the course of functions is polynomial-based functions, which they could be beyond this, of course, but they would be a non-negative integer, which is here. I'm sorry, I don't want to confuse it with absolute value. That's what's up here, but a non-negative integer based function would be a whole number 1, a whole number 2, a whole number 3. And in that event, you would have something that would be linear, square, and cubic. A reciprocal function would be the instance when you have a negative. So it would be, you can write it in the style of an integer, so -1, or in the more obviously rational form, which would be 1 over x. Radicals are when you don't have a whole number, you have a fraction here. And then you have the index over the exponent, or under the exponent, I should say. And something like a square root would be, instead of writing it x to 1/2, it would be an index of 2, which gets neglected. You know, a lot of times that's almost never written. I do. I think it's better, but it's the original concept, so they leave that out. Just like 1s often are left out. A type of square function, I would argue, is a quadratic. I think some people might argue with me and say, well, isn't it the other way? I think a square is the most basic type of thing with an exponent of 2, right? When you think quadratic, you generally think something that is polynomial in the more obvious way, you know, a trinomial, I should say. So 3 terms, right? There's the general form of a quadratic. There's something known as the standard form, which, if you analyze it, is strikingly similar, probably by no coincidence, to the transformation model, right? There's an h value, a k value, and at least an a, right? This is also known as the vertex form because the features that would be sitting in h and k, a stand-in for x and y, they are the point of the vertex of the parabola that squares make, right? And then there's another form known as the intercept form, which is a completely factored form, right? This is beneficial if you're trying to look for the X-intercepts because the p-value and the q-value essentially would be the X-intercepts. Right. Anyhow, that's the logic for today. We're still dealing with algebraic functions, specifically the polynomial-based type of degree 2, otherwise known as square, right? And then the sort of creme de la creme amped up version of square, which I would argue is the quadratic, right? The trinomial-esque, all right, at least to begin with. All right, now, switching gears, all right. Here is another slide to expand upon that. An overview of the quadratics. Yeah, I'm going to zoom in on this because it's really just this portion of it that's relevant. All right. The general form is not factored. It's most obviously a trinomial, ax squared plus bx plus c. And if you're wondering, hey, wasn't that called standard form elsewhere? Why are you calling it general form now? It was. This is known as the standard form, this trinomial, where it's set equal to 0, and we're just merely talking about equations. If we're talking about functions per se, then they use that phrase instead, general form of a quadratic function, right? The word standard form is instead reserved for things that don't look like that. It's a little confusing, granted. That's why I personally, I like to go with the alternate nomenclature, the vertex form. Why? Because that's its job, basically. Right? If you think about it this way, is the general form is not factored at all. It's pretty much as it is, a trinomial on the, as far as the expression is concerned. And the vertex form is partially factored. Then the intercept form would be completely factored. And again, there are different benefits to these two, at least. All right, something that is in the vertex, i.e. standard form, tells you the location of the vertex. All right, remember this is a stand-in for x and that's a y, essentially. All right, remember the equation of a circle, right? Same labels, h and k, not sure why. All right. The intercept form, which again you're not really responsible for, in the forthcoming conversation, when we get to rationals, it probably would be to your benefit to have this as a reference at least, though. Something that was taken the whole 9 yards and completely factored, all right? What this reveals are the zeros, right? The zeros is an alternative labeling for the X-Intercepts. All right. If you had to draw a picture by hand, you might want to know where that is. It helps flesh out the graph. All right. Specifically, the p-value and the q-value, again, weird labels perhaps, that would be the X-intercepts respectively. All right. Do beware. There are some examples of a quadratic function, namely that parabola shape, that you don't have any. All right. And the factoring, if it can't be factored, would probably reveal that. Remember, if you can't factor, but you're still looking for a value of x, you have the quadratic formula still from, earlier, chapter 2. And that would indicate whether you have a real x value or you have an imaginary x value. All right? If you don't have real values, you don't have x-intercepts. Now, this is the last tidbit here. The Y-intercept, which is something you could get by inserting 0 and x, just as always, and the vertex are sometimes the same location, but not always. Okay? Now, as far as the graphs look, what I should probably do is just maybe above these draw some simple graphs for reference, to build up the reference. So I'll do that. Maybe a little bit of light, not too much. Okay, 'cause I can't see. All right. If you have the space either just above or just below on the paper, and you want to add this reference, draw 3 cross shapes. All right. This is a y value and x value, y and x axis. Origin. All right. Some things that you could tell immediately just staring at this in the general form. If it is an exponent degree 2, then you know that it is a parabola of some sort. All right, so you would expect that shape, parabola. All right. If it happens to be a positive on the lead coefficient a, then you know that the arrows are pointing up. All right. Okay. If you have something in the standard form, what you could tell right away is that, yes, it's degree 2, so you are going to anticipate the same situation, that if it's a positive lead coefficient, it would be opening up. If it's a degree 2, it is indeed a parabola, all right? But if it has this partially factored form, and there is an obvious number here and here, then you would have a parabola, but it might be shifted over to some other place. HK. Remember, the H value is unfortunately counterintuitive, so even though you might see minus here, just understand that it means it's standing in place of X value, and normally we think positives, you move to the right, right? But if you see a minus, it's counterintuitive. That would be really indicating a positive. You kind of read it like this, that whatever the number is sitting here, and in the case of K, the Y value, you associate the sign with that, but not with H. Okay, so that would reveal the vertex, right? If you were to go the whole 9 yards, as I mentioned, and you have an intercept form of the quadratic formula, of a quadratic function, again, there are some things that you could figure out. It is a little less obvious in this case because it is completely factored. But if you see that this is degree 1, x here and an x here, you might go, well, if I foiled it, it would be degree 2, all right? And this is a positive up here, so yes, it would be the same situation of upward pointing arrows for degree 2. But what's more interesting is that if it's completely factored, it will reveal again the x-intercepts. So you might see something like this, all right? A parabola where, I probably should have used green, right? For the sake of consistency, let me do that. Come on, let go. There you go. So you can see a parabola shape, and there would be an x-intercept and another x-intercept. So that's where the point of the parabola cuts through. Let's see if that's a little bit better to view. And one of these is the p-value, and one of these is the q-value. All right. P and a q, all right? Hypothetically, if you had, say, something like this, x plus 3, and x minus 2. One of these would be, if it's a positive, 3, it would be like a negative 3. And if this is a negative 2 or minus 2, it would end up being positive 2. Okay. And again, you take those values and you position them here and here, respectively. All right. It's an X-intercept of 0, an alternative label, if you will. And therefore the y coordinates would be zeros. Okay. Okay. All right. Move this now. Now are we on time? We're doing okay. All right. Let me show you another graph. Pardon me, another copy here. Here again is a list of the key features of a parabola. This is the whole thing. So, humor me, I'm going to have this zoomed out for a moment because I want to annotate here. If you wanted to sort of form a procedure, if you will, for graphing, if you're going to do it by hand, and you don't have to, you of course have your graphing calculator, this is the order in which you might do things. All right. Analyze the lead coefficient. If you can see, this is the positive a, negative a. If a parabola shape is something like a tulip, if you will, opening up, quadratics make that shape. It's sort of a hybrid of a u and a v. It's neither of them. V, remember, is the absolute value, and u is something that doesn't have a point. Well, parabola does indeed have a point, but it doesn't have flat sides. It has curves. So it's something, the bastard child of those two things, right? Anyhow, the lead coefficient, if it's a positive, degree 2 functions, would have arrows opening up, so the flower, you might say, is blooming. Right? And if it's a negative coefficient, remember that causes a vertical reflection, so it would be essentially facing downward. So something like a flower wilting. Right? I would say, think of this as being step 1, and this, what's following, is also step 1, because the positive is attached to our number, ultimately. If you have a fraction, just to simplify, that is something between 0 and 1, right? What you would expect in the case of a parabola is that it would be a little bit wider, actually. So, looks like the blooming onion now, right? Sort of pops a bit. If you have something that's greater than 1, perhaps again ironically, it is something a little bit narrower. So you'd see something like that, right? Then when you get down to the vertex, right, depending upon whether you have something already in the general form or already in the standard form. If it's in the standard form, you're good to go, all right, because you could just pluck out the information that would be the location of the vertex. All right. This is really step 2 collectively. If you have the general form, there's a formula for calculating the X-intercept. There is actually a formula that you could calculate independently of the vertex X coordinate, but it's maybe more trouble than it's worth. It's more complicated than just this formula for X and then evaluating the function at that point. Once you have the X value, you essentially evaluate the function at that point. Okay, and that spits out your Y value. Honk honk. Then there's something known as the axis of symmetry. The axis of symmetry is essentially an imaginary line that would go through the vertex. So if you know the location of the vertex, the axis of symmetry would be easily determined from that. It would be a simple equation that is a vertical line equation. So if it's a vertical line equation, it is x equals whatever the value of the the x-coordinate of the vertex. So x equals some number, essentially. If you said that the vertex was at the location of x-coordinate 3, comma, whatever, for the y-coordinate, then the vertical line equation would just simply be x equals some nice satisfying number, right? And you would just simply draw a line through that point, right? Then there is, to flesh out the picture, some extra points, the X-intercepts and the Y-intercept ultimately. Remember, to find the X-intercept, it's the same old shtick. You put 0 in place of y, like you would with linear equations. And for the Y-intercept, you put 0 in place of x. Right? Again, also like for linear equations. Right? So this would be essentially step 4 and step 5. Right? Okay, let's do an example. All right, I'm going to move this out of the way and put some graph paper up. There. Oh, okay. Let there be light. Okay. Say you had to graph this by hand. The function of x is equal to 3x, 3 parentheses x rather, plus 1 square minus 3. Okay, and I'm just going to slip underneath it a model that is good to compare to, x minus h n plus k. Right? Transformation model, otherwise known as the standard or vertex form of the quadratic function. All right, so if I'm going through the list here of good things to look at, identify really whether you have the standard form or the vertex form. Right? This you might recognize as, standard is vertex, standard or general form. This is the standard vertex form. So there's a couple of things immediately that you could tell, all right? This is the lead term A, coefficient A. This is the H value, and this is the K value here, all right? I'll put some bullets over here. The A value is positive 3. So what you can anticipate as a result of that is that the arrows will be up. All right? A lot of times when they draw these graphs, somebody will simply sketch out arrows like this, since they know that it's a parabola. It doesn't end up that they're going to be here and here respectively, but just to give you a sort of inkling that they're upward pointing. All right, so arrows pointing up, and because it's a 3, it should actually be narrower than usual. Okay. So you can expect it maybe a little bit skinnier like this. All right. Let's see. Number 2, since it is in the standard form, right, the location of the vertex would have to be h comma k. All right. Remember the h is counterintuitive. So if you see sitting in place of the h, there's a positive 1 there, all right, it really should be negative 1, and then whatever the k value actually is, which is minus 3. All right, at this point, you can insert that in the graph, all right? So from the origin over negative 1, down 3, 1, 2, 3, you have a dot already to help flesh out the picture. All right? To get it a little bit more precise, though, you need more points. So The next thing might be that you're looking for the axis of symmetry. All right. The axis of symmetry, which is good to know, right, would be through the vertical line x negative 1, right? Of the vertex coordinate x, right, there would be a vertical line simply known as x equals negative 1. So you would put a line through here. Right? I'm just going to not to have to dig up my ruler here. I'm going to draw a very faint dashed line here. Right? This is the axis of symmetry, and this is the vertex. Okay. Then the X-Intercepts. Right? I'm a little short on space, so what I'm going to do is the X-Intercepts. All right, remember that means that you're going to stick 0 in place of y. So if the function of x, it's in function notation, but if you just simply call this y equals that, then you would park a 0 here. All right. So that means 0 is equal to 3 times x plus 1 squared minus 3. All right. You can clean up one side, all right, and then rearrange things to solve for x. Let's see. All right. When you have x plus 1 being squared, remember you're going to end up with the perfect square trinomial model, which means the outcome of just straightening up this bit of it, x plus 1 squared, is that you're going to get x squared plus 2x plus 1, still inside the parentheses because there's a 3 to distribute out here and a minus 3 here. All right. Then you would distribute the 3 to each of the polynomial terms, so you'd end up with 3x squared plus 2x plus 1, and then there's this hanger-on minus 3 here. And if you subtract those, oh, sorry, ding dong. 3 times 1 is indeed a 3. The 3's will cancel, right? So that leaves you with this, 3x squared plus 2x. And since this is equal to 0, because that's standing in place of y, and y is standing in place of the function notation, then you have this equation. All right. Now, my instinct is to try to factor this now, and then apply the zero product rule. Does that work 100% of the time? Well, for things that are factorable, yes. The common factor is an x value, so it'd be 3x plus 2 is equal to 0. Oh, ding dong again. I'm sorry. 3 times 2 is a 6. I'm wondering why that changes things. All right, there's a 6 here, all right, which makes this a lot easier to factor. I'm wondering why I'm going to get 2/3 as a fraction. Shame, shame. 3x can be ripped out then of both of these terms. That leaves you with just x here, and then plus 2, thankfully. That is a lot easier to factor. All right. Okay. So if you apply the zero product rule at this point, right, you have factors that are 3x might be equal to 0, and factor of x plus 2 is equal to 0. All right. Which means that if you just move the 3 as a coefficient of x over to the opposite side, it would be 0 divided by 3. So x would be equal to 0 in that instance. And in this case, I'm only skipping steps for the lack of space. You would subtract 2 to the other side, and then x would be equal to negative 2. And we're good to go. Okay, now, since that's what the values of x's are, when y is 0, then pair them together each as ordered pairs, right? This would be the ordered pair 0, 0, the origin, so you'd have a dot right there. And this would be the ordered pair of negative 2, 0. which would logically be there because it's symmetrical, right? The benefit of having an axis of symmetry is once you have one of these, if it's on graph paper, you could deduce that, well, from the X-intercept to the axis of symmetry is one space, right? And because it has to be symmetrical, it would logically be there, okay? You have enough information, right? You could, if you wanted to get it very perfect, all right, get some more test coordinates, right? Now, look what happened. The X-intercept is at the origin. So if we were looking for the fifth thing in this list of things to do, because this is the fourth, the fifth thing would be looking for the Y-intercept. And in that instance, again, you're going to put 0, pull the old trick, you're going to put 0 in place of X. That's really easy, right? If you put 0 in place of X, then it would be 3 times 1 squared minus 3. And just for the sake of space, I'll write it here. Y would be equal to 3 times 1 squared minus 3. 1 squared is 1. 3 times 1 is 3. This would be 3 minus 3 again, which is 0. The Y-intercept in this particular problem is the same as the X-intercept. So they would be in the same location. Okay? And that's it for the test coordinates here. All right, you could do more, but here's your parabola. Something relatively narrow, sorry for the sloppiness, and it's pointing up like so, blooming, right, rather than wilting. All right. All right. Let's do another. In a full-size classroom, it would be to my benefit to have an extra board here. It's not to have to draw on top of the picture. But preserving it in the process. Okay. So let's say that you were going to graph something that looks like this. The function of x is equal to x squared plus 4x plus 6. All right, and again, here's the model for reference. ax squared plus bx plus c. This is what it most closely resembles. The general form of a quadratic function, right? So there's little bits of information that you could pluck out of this, all right? Well, once again, it's degree 2, so it's definitely a parabola, right? It's apparently a positive 1 up in front, so the a value is upward pointing arrows, all right, and it's sort of more or less normal, right? So it's neither wider nor narrower, all right, than a parabola would be, all right, barring some other conditions. Let's see. Now, if you have decided that this is in the general form, and that would be correct, all right, in a case like that, to find the vertex, you're going to have to incorporate this formula. The x value of the vertex is negative b over 2a, right? So you look at this compared to the general form, this b value would be 4, all right, and the a value is positive 1. If you substitute those, all right, a 4 here and a 1 here, it is essentially negative 4 over 2, which is negative 2, right? That's just the x though, right? So what we would need to do is then evaluate the function using negative 2. If I go back to this and I stick negative 2 in here, that means, I'll erase this just to get out of the way. that in place of the first x, I'm going to put -2 to square. In place of the second x, I'm going to put -2 to multiply by 4. And then follow the order of operations, which means that you should square first, so this is a 4. That would be -8, and this would be +6. Adding and subtracting are equally important opposite operations, so you work from left to right. This would be -4 plus 6, and that should be 10. Where's my suspicion rule? Okay. Oh no, I'm sorry. I'm adding. I shouldn't be. -4 plus 6, one of each you subtract, not add, so that's +2. Okay, cool. So if you have for the y value +2 and for the x value -2, then the vertex is at -2, 2. So you go back to the origin, count 1, 2, and then up to 1, 2. All right. A couple of things, just for the sake of, expectations. All right. We already know that this is an upward pointing parabola, so there'd be arrows, something like this and this. Right. And notice where the vertex is. Right. What you should anticipate is that if it is in fact oriented this way rather than upside down, so blooming rather than wilting, there's going to be no X-intercepts in this case. You will nonetheless prove that if you go through the motions. All right, let me complete this thought though. If we have the vertex, then we know that the axis of symmetry should be the vertical line x is equal to the x coordinate, so -2. There would be a dashed line running through that point of the vertex. Okay? If that's a little bit faint, I'm going to use this a little bit darker here. Green is always questionable marker. Why? All right, so there's your axis of symmetry. All right. To get the x-intercepts, again, ordinarily, and I'll use green. The x-intercepts, the zeros, again, you would put 0 in place of y and then solve for x, right? If the function of x is a stand-in for y, and you put 0 in place of y, then you have this. 0 is equal to x squared plus 4x plus 6. Right? I would attempt to factor it first. You're going to try, like if you sort of jump the gun and you go straight for what would be a binomial times a binomial, I wouldn't fault you for that really. You'd go, well, it's x and x, right, for x squared. But what makes 6? 1 times 6, which if you subtracted them would only make 5, and 2 times 3, which would still make 5. All right, so you're not going to get 4 no matter what you do, which means that it can't be factored. It's prime, right? Therefore, you would have to use the quadratic formula, right? Really short on space for that. So I'm going to put it over here. The quadratic formula is, of course, to solve for x is equal to -b plus or minus the square root of b squared minus 4ac over 2a. And yeah, you have the values a and b's and c up here. All right. A is, without the mess in the way, 1. All right. So you would put a 1 here and also there. And the b value is 4. So you would put a 4 here and a 4 here. I would normally put parentheses just to be careful with the signs. And then the c value is 6, right? So you have the 6 here. It's a bit messy. All right, remember, you should lock your focus really on this portion of the quadratic formula because that will ultimately tell you whether you have something that is real or imaginary. Namely, if you get a negative underneath the radical symbol, you're going to get an imaginary, which means there's no x-intercepts. So the way that the math would work out, right, is that you would square this 4, and underneath the radical, then you would have 16 here, right? Then if you multiply 4 times 6 times 1, you'd get 24. So 16 minus 24, what are you going to get? A negative 8. A negative 8, if you were to go through the motions, and it would be kind of pointless because it's imaginary, all right, would be factored as the square root of 4 times the square root of 2 with a little I out in front to account for this being a negative. The square root of 4 would be 2, right? And you'd end up with this. X is equal to negative 4 plus or minus 2I square root of 2 over 2, all right? You could try to simplify this a little bit, all right? And then x would be equal to negative 2 plus or minus I square root of 2. But again, this is not real, all right? So it's imaginary, all right? It's a complex number, all right? So that, in our case here, just proves something that we were suspicious of already, or that we would be suspicious of, is that if you have a parabola that is essentially running like this, there are no x-intercepts, right? Because it's not touching the x-axis, it's above the x-axis, right? That just validates that suspicion, all right? If you now look for the y-intercepts, that would be a little bit easier, right? The y-intercept is, again, pulling the old trick of putting 0 in place of x instead. So that's super easy, right? Right? Especially in the case of this general form, right? If y essentially is equal to x squared plus 4x plus 6, and you put a 0 intentionally here and a 0 here, that term goes away, just left with 6, which means that the location of the y-intercept would be 0, 6. Right? 0 up 6. 1, 2, 3, 4, 5, 6. You'd have a dot here, and you'd have this much of the graph. Right? Now, you could do some test coordinates, which is plug in a different value for x, and then you could establish more points along the curve, right? Or, in this case, a perfect example of taking advantage of the fact that this is done on graph paper, and that you know that parabolas would be symmetrical, and you have the axis of symmetry. How many blocks wide is it from this point to the axis? It's just 2. So 1, being that it is symmetrical, would make the assumption that there has to be a point here, because that's 2 blocks this way from the same axis of symmetry. And that is enough to draw the picture. You'd have a symmetrical parabola of pretty much a normal width. Okay. All right, let me show you something, because more likely you'd be doing this with your calculator. And I made a sheet for that. No, not that one. Okay. If you wanted to graph something naturally that is a regular equation, right? Let me get the gobbledygook out of the way here. That's a bit too you know by now probably that if you have a graphing calculator, TI-83 or 84, you press y equals and you enter the unique equation expression, and then hit the graph button and it will draw the picture for you, barring some fine tuning, which again is either the window button for a manual and the zoom for an automatic, if you will. All right. If you wanted to graph inequalities, all right, or in theory you wanted to graph x, which you could superimpose upon that graph, a regular graph, all right, provided the software is up to date, all right, if you press the apps button and you scroll down to where it says Inequalities, all right, and you could get to essentially something that looks like the y equals, but it'll either be an x up in the corner, or it'll be inequality symbols that you have, right? And then you would press graph and it would superimpose pictures, right? That's kind of a neat feature. What we're interested in right now is essentially these things. If you wanted to look for the x and y intercepts, sort of a more brute force way, once you have the actual drawing, if you hit second and then graph, you can get to something that is a table of x values and y values. And you would see, you could basically look for the zeros, right? And that would tell you, depending upon whether it's in the first column or the second column, where the x-intercepts and the y-intercepts would be, right? Let me give you an example here. Let me enter a graph. I'm just going to put x squared, maybe plus 2 to make it interesting. I'm just entering this random parabola here. I don't want it to have a negative though, that's silly. Sorry. Alright. Here I have a parabola entered, and I hit graph, and there's the drawing. Neat, right? If I hit second and then graph to engage the table feature, right, you could run through this, right, and look for zeros, right? So I'm reading it backwards, unfortunately. It's not showing me a 0 for the y, which is disappointing. All right. The alternative, all right, is stop doing that. I'm sorry. I'm pressing the buttons while I'm doing that. Alternatively, if this yields no a help here, no zeros as you scroll through these. All right. I seem to be off the scale here. Sorry. Go over to the X ding dong. There you go. Going down. Then when you have the graph, all right, if you hit second and then, well, if you just hit trace, I should just do this, all right, you can enter 0, all right, and see what it would be for the x value, the y value. So if you're at, you see the coordinates at the bottom here, -1x is y equals 3. Well, what would it be if you put 0 in for x, right? Gives you 2, right? There's more than one way to do it, right? This is for sure, right, more to your benefit. Let me pull this back down. If you're looking for just the x-intercepts, there's a feature in your calculator that you can get through second trace to engage the blue calc. And then option 2, I want to say something like that, is zeros, all right? It's another example of where you have to move the cursor to basically tell your calculator where to look, all right? Anyhow, that is, if you don't have something like this to begin with, or if you were trying to write something like this, the intercept form, all right? You can have your calculator tell you what the P's and the Q's would be, right? So, in an example like this, there would be no x-intercepts because it's not crossing the x-axis, it's above it. So I'd have to try the problem from earlier. Yeah, I'm just going to randomly stick in the intercept form of something, and not too complicated. So x minus 3 comma x plus 2. Okay. If you had the intercept form in theory of a quadratic and you just entered it, here's the drawing. No. Graph, please. You can see that it penetrates the x-axis, right? Now again, to prove a point, if you wanted your calculator to give you this much information, right, you could make a prediction based upon what you're seeing here, where you could have it tell you, right? Say you hit second and then trace to go straight for the calc features. Say choose option 0. Again, you have to move the cursor around to tell it where to look. You're zeroing in onto a little bit of, around where you would expect the x-intercept to be. So I'm going to scoot this up. That would be as far to the left as I wanted to look. Then you say enter. And then just a little underneath there. And then say enter. And then I ask you somewhat redundantly, do you want me to guess? And you go, yeah. All right. It tells you y is 0 because it's an x-intercept when x is equal to -2, right? That's only one of them, right? And then you go through the motions again. So you would hit second and then trace, option 2. Again, in this case, you're going to scoot over to here. As far to the left as you want it to look is just underneath that point of intersection. And then just a bit over it is as far to the right as you want it to look. And then notice the arrows up here. That's you squeezing, you're making the calculator squint, if you will. And then you go, yes, guess please. And it tells you y is 0. I don't have a fingertip, I'm sorry, I have a weird looking finger. X equals 3, all right, is the x-intercept, right? So essentially your p-value is 3 and -2 respectively. So if you had something like this, right, the negative value, you might slip in here, all right? So you'll put -2. And then the positive value would slip in here, all right? Straighten up the arithmetic here. And you'd have x plus 2, comma, x minus 3, right? An intercept form of a quadratic function, right? All right. If you want to get to the vertex, all right, there's another name for the vertex. There always seems to be another name, right? And that would be a minimum or a maximum depending upon whether the parabola is facing up or it's facing down, wilting or blooming. So, once you have your parabola entered into your calculator, again, you can hit second trace to engage the calc feature and then choose what you expect is either the minimum or the maximum. So in this case, you would hit second, trace, and then you notice the options 3 and option 4. Now, since the parabola that I just concocted looked like this, basically, it's upward pointing, all right, you would expect that this is a minimum, okay? Not a maximum. So don't choose maximum when you're asking it because it may give you an error message. All right, choose minimum. All right, so 3, and again, you got to tell it to where to look. So you're going to scoot down here, looking at it backwards. So the left boundary would be somewhere around there, the low point, what you expect, and the right boundary somewhere around there. And you tell it to guess, and it gives you some figures. All right, so 0.5, so you'd expect it's something like a half, all right, and then it looks like it's -6.25, so 6 1/4, all right. So 0.5, yeah, 0.5, 6 1/4, just to cleaning up the extra zeros here. All right. How would you get to that the more brute force way? All right. Again, if you're looking for a the vertex point, you would have to stick in A, B, C value into, well, A and D specifically for the vertex formula for X, and then evaluate the function using that number. Right? Otherwise, translate the thing that you have into the vertex form. Okay? Alright. How are we on time? We're okay. Alright. Let's say hypothetically that you had to write an equation. Let me put some graph paper back up here. Just had trouble here. All right. Suppose you were given this picture. Suppose you were given a graph and you wanted to try to write an equation. It's probably easiest to start with the model that is the standard of vertex form. So let me begin with that. A, x minus h, n plus k, right? Here's a general transformation. Let me just that. You can zero in on this much of the graph here and determine what the vertex point would be. I probably should start with A, but I'm not really sure what the number is per se. I just know that it would be positive because of the orientation of these arrows. Right? Anyhow, the vertex would be easiest, right, because it's the low point of the graph. And therefore it would be the location of -2, -3 in this case. Right? The k value is -3. The h value, standing in place of x, would be -2. So there's a double negative there. Right? And that means that you have ultimately x plus 2. Right? Right. Another thing to tweak, right? You have, instead of an n for the integer here, you would put 2 because it's a parabola. Right. That would leave you basically with the value of a to calculate. Change this to y. And then use some other point use one other point on the graph, on the function, to solve A. Alright, in other words, where else do we know, based upon this being on graph paper, that there's a point that makes up the curve here? Alright, I put this at the Y-intercept here. Alright, Y-intercept is a very convenient one. How come? Because the x value would be 0, so that would simplify the arithmetic, right? It's strategic to do that, right? Y-intercepts are a good choice, right? Because it's going to be 0 for the x value and then whatever the y is, all right? So over here, this y-intercept would be 0, -1, right? Those are very good numbers, right? Because aside from it being negative, it's just 1 and 0, to put here and here respectively, right? Leaving you with just A. So, let's see. If you put a 0, put a -1 in place of what would be y, and you put a 0 in place of what would be x, that means that you have -1 is equal to a times essentially 2 squared plus, minus 3. Okay. Square those 2, you get -1. This is a 4 minus 3. -1 is equal to 4a minus 3. And then you have a linear equation that you can just manipulate the normal way, build a little table. Add 3 to scoot it over to here. Cancel. This would be positive 2 is equal to 4a, and then you would divide by 4, and then you get a in simplest form is a half, and that ends up being a positive. Which means the function of x would be equal to 1/2 x plus 2 squared minus 3. Okay. I'm getting delirious from the heat here. Turn this off, and I think I'm pretty good with my projected today, so I'm going to put that off and spin the bulb here. Alright. Thankfully, so much more light. Okay, let's go through, let's say how to convert from what would be standard form to general form. Essentially what you'd be doing is you're going to FOIL distribute and simplify. I think this red marker might be done for. Alright, so I'll keep that over here. The last problem, the thing that I just concocted looked like this, right? The function of x is equal to 1/2 times x plus 2 squared minus 3. This is the standard form. Let's say that you wanted to put it in the general form. All right. What's going to happen virtually every time is that since you have this binomial squared, it's going to end up being or emulating the perfect square trinomial model. All right. So if you analyze what the two features are here, an x and a 2, right, the perfect square trinomial model predicts that you will have x squared, and on the very far end, this number squared, which would be 4 in this case. And then the middle would be twice these two terms. So it would be 4x ultimately. There is meanwhile a 1/2 sitting out here and a minus 3 sitting out here. All right, so having FOILed, if you didn't write x plus 2, now you're going to distribute There's a prison break going on somewhere. Hear the sirens. A half times x squared, a half times 4x, and a half times x. First, because it's multiplication, distributing. And that means that you have a half x squared. A half times 4 would be plus 2x. A half times 4 would be plus 2. And then there happens to be this minus 3 that's sitting here, which means that ultimately this would reduce to, the function is a half to the lead term coefficient of x times x squared plus 2x. And then this is just minus 1. Okay. All right. For argument's sake, what if you had to go the other way, right? From general to standard, right? You already know what this particular problem looks like in both forms. I'm going to start with this one to prove that you can go back the other way. In that case, there's two choices about how you would go about it. One is very interesting, because it involves the technique known as completing the square. But it might be, you know, sort of swatting a fly with a bazooka, so maybe more trouble than it's worth. Let me just give you sort of an overview. If you want to go from general to standard, all right, you have basically two choices. All right. The more sort of elegant, perhaps, would be the word, is try to factor, right, and then employ something known as completing the square technique. And then simplifying. And this is really the essence of it. Completing the square. All right? Everything else is just gravy. All right? The probably more efficient way, and what I would encourage you to do, is to employ formulas. All right? All right. The good news is that A is A, right? So if you know what the A value is here, then the A value would be the same in the standard form, right? The other thing to consider is the H value, right? The H value is really the X of the vertex. Right? And there's a formula for that, which is simply negative b over 2a. I'm going to write this up here just to save it. A half x squared plus 2x minus 1. All right. To get the k value, the k value is the y of the vertex, of course, right? And that is really just the function evaluated at x. There is a formula that looks very similar to this, that is involving b's and a's, the coefficients in the general form. But it's probably more trouble than it's worth. It does exist, and I would be remiss not to just say that to you. But probably, again, for the sake of efficiency, whatever you calculate this number out to be, you're just going to plug that into the function, and it will spit out what the y value is. So I would go about it this process just for the sake of timeliness. Anyhow, we already had this in standard form, but just to prove that you could go back the other way, humor me. Let's see. Start with the model. a times x minus h squared plus k. All right. We already know what the a value is in this case. So that's ax squared plus bx plus c. A half is what the a value is. So you would park a half right there. This much will not change. The h value, again, would be the vertex x, so we're just going to insert it in this formula. The b apparently is a 2, so you would put a 2 here. And the a value is a half, so you would put a half here. The outcome of this is that the 2's would cancel and you're just left with 2. Of course, it would be negative 2 because of the formula. All right. So you would put a negative 2 there. Right. And then you would evaluate the function in this form using negative 2. So, just for the sake of space, sorry. You would stick a negative 2 here and a negative 2 here, and follow the order of operations because you're just dealing with the 1/2 of this. You're not moving things. Right? If you square negative 2, then it's going to be a half times 2 squared, which is 4. All right, half of 2, pardon me, half of 4 is 2. All right. 2 times negative 2 would be minus 4, and there happens to be a minus 1 here. Positive 2, because it was squared, all right, and so the minus 4 would be negative 2 minus 1, which is 3. Okay, this is negative 3, all right, so that would sit here. And then ultimately you have the thing from earlier. Right. A half times x plus 2 to simplify squared minus 3. Okay. What time is it? Okay. All right. If you're curious, I'll do it the other way, but let me try different problems. It's getting boring. Let's say that you would convert something like this. The function, this will be a different one. I think I moved my board just a little too much. Two x squared plus 4x plus 3y. All right, and you want to convert this to the vertex form, standard form. Basically, you're going to zero in on just the expression half of this, the rule. Right? Pay attention to basically this side only. All right. All right. And it's a little weird. All right. You're going to factor, which means you're going to put things in parentheses, right? The first 2 terms only, right? Which means just pay attention to these 2 chunks of the 3 of them, right? Factor just those, right? They're both made of the letter X, that's the reason, and they're both made of the number 2 somehow. So in the factored form, what you would get is 2x on the outside. Or you could just take out the 2 rather. Yeah. I'll just take out the 2. X squared plus 4x. I'm going to purposely leave a space here, and there happens to be a plus 4 here. All right. This is where completing the square method would begin. All right. If I missed one thing. If I just took the 2 out of both of these things, that would be a 2 there as well. Sorry. All right. Now, the completing the square portion of this would again be, you are creating a term here, right? Why? Because you want it to be factorable. So when you try this completing the square method, you're making something that would be factorable. It involves taking this middle term, dividing it in half, so coincidentally it's the same number 2 here, and then whatever the result is, squaring it, all right? Divide by 2, the middle term, all right, square, and then you would park it here, all right? What's 2 divided by 2, right? This would be just 1. If you then squared 1, it would be 1 squared, right? And then under normal circumstances, like when you're trying to use this to solve, right now I'm not solving, I'm just sort of manipulating the situation, you would write this here, all right? So plus 1 squared, right? Which is really just the number 1, right? Right? Because you're messing around with this, right? You can't just throw a number in there that didn't belong, right? What you have to do, and this is the legalese portion of this that maybe drives a person crazy, which is that, yeah, I created this because I definitely have a reason for it, right? But in order to get away with it, I have to do this additionally. Put in the same thing that I have inserted here via completing the square, all right? I'm going to also put this negative incarnation of it. Why? Because ultimately what that means is something minus itself is 0. I'm not really changing the value of anything overall. Okay? That's cuckoo, I know, all right? But I also, let me put here just for a note, all right? Also put the negative version of this, all right? This makes it legal. 0 overall. This is dying too. All right. Adding 1 to something is not legal by itself. Adding something and then subtracting it immediately after, that's legal because what's the sum of these things? It would be 0. It's just merely changing the appearance of something temporarily. All right. All right. Now, what you're going to do is redistribute, all right, at this point. Right, so what does that mean? It means distribute the 2 back now, back to this, and to each of these versions of 1 that you I just concocted, right? Which means that this would be 2x squared again, all right, plus 4x again, all right? And then, since 1 squared is really just 1, 2 times 1 would just be 2 now, all right? And then the negative version of it would be an additional minus 2, all right? And then there's this 4 that's still hanging on here. It's a minus 4. I should have made that to begin with, sorry. Invented a problem, sorry. Now, what you end up with is 2 chunks that you want to simplify. All right, I had to unfortunately distribute in order to get this trinomial together and then this other chunk together. And again, I'm sorry, the original problem that I was borrowing this one was in fact a minus 4, so please make that alteration. All right, heat stroke. I'm gonna blame the heat now. Minus 2 and minus 4 would be minus 6 ultimately. Okay. Now, as cuckoo as it is, right, you're going to factor again, right, just this trinomial. Chunk of the whole, right? This is not too bad, right, because it has the obvious coefficient of 2 again, which means you could rip that out, right? 2 distributed would be x squared plus 2x, right, plus 1, right? And it just so happens, and that's what happens every time you employ the completing the square method, is that you get something that after I've factored out a monomial, you end up with a perfect square trinomial, right? Which means that if you were to take this trinomial and then make a binomial sitting next to a binomial, they're going to be identical, right? So essentially, this, without necessarily going to this step, right, x squared and 1 and 1, these would both end up being identical, x plus 1, x plus 1. This is totally intentionally so. All right. Why would anyone bother doing that? Well, because if you have identical binomial factors, you have the perfect square trinomial, which could be simplified even further still, writing an exponent rather than 2 incarnations of this. All right? Which is why what you end up with in lieu of that is this. The standard form of this original, which is 2, the thing hanging outside here, otherwise known as the a value. This binomial of x plus 1, simply written one time, acknowledging that there are 2 iterations of it, 2 clones, if you will. This would be squared, and then there's this minus 6. I would advise a person, naturally, again, for the sake of timeliness, again, use the formulas. But as is often the case in math, there's more than one way to do something, right? And this is kind of a fun mental exercise. It's the only reason that I'm showing it to you. Now, if you want to prove that this and this are in fact the same thing, right? You can take a calculator, enter this, and then enter this right underneath it, and you'll see that the graphs overlap, right? So I'll do that. Two x squared plus 4x minus 4. Here's the original. 2x squared plus 4x minus 4. That's the original incarnation of this in general form, which would graph a parabola that looks like this. Okay. If they are in fact, if this is a correct translation to here, when I enter this underneath it, what you'll see is that there'll be no change in the picture. So, assuming I did this correctly, x plus 1, and it's always good to check, right? This is what I predict this would be in the standard form. If I hit the graph button, there should be no obvious change. One is overlapping the other, and there isn't. It's correct. Good. All right. All right, here's the last thing, and it's kind of just a bit of theory. It has to do with the domains again. When we're dealing with the parabolas, domain range, here's what to expect. All right, put the domain over here to summarize, and the range over here. All right, remember, what is domain? Basically, X is allowed, or what is possible. What is the range? It's the Y's that are allowed or possible. Because parabolas come from a square function, a simple polynomial, all right? What you can expect is that you'll have graphs that look like this, right? You're either going to get an upward pointing parabola or potentially a downward pointing parabola, right? But in either case, were you to analyze the x's, what are the x's that are possible? It's a little disorienting because of the nature of the curve of it. You know, just look at things one-dimensionally, but you have to try to stretch your mind that way. All right, if you analyzed any of the x's of which these dots would be made out of, they would just be getting, you know, although they're curving upward, they're still stretching out this way, the x's, all right, and in the opposite direction. So that means infinity towards the right and infinity towards the left, right? Ultimately, the x's, right, would be all real numbers are possible. There's no holes, right? Unless there is a situation where there's some kind of a hole that's described, but that's not in the general case. There's no holes, right? If you were dealing with the y values, on the other hand, because of the nature of the parabola being curved, and it comes to either a low point or a high point, if you will, there's going to be some limitation there. Here's two simple graphs. Right. What's important to note is the vertex in each of these cases. The vertex in the standard blooming upward pointing parabola is in fact a minimum. Right? And the vertex in the sort of wilting incarnation of a parabola is a maximum. Okay. So again, if a person were to analyze any of these dots of which this function is made out of, specifically for the y values, right? The y values will go up into infinity, all right? But they come to a crashing halt when they hit the minimum here, all right? So insofar as the range is concerned here, the y is known as the range. It will be different in each of these cases, right? The y values would start basically at a point. It would include the minimum value because there's no holes, right? But the abbreviation for this in interval style would be whatever that y minimum is. The y coordinate of the vertex, right? Whatever that y value is there, comma, into positive infinity curve, right? Remember, infinity is not a specific place, right? So there would be a bracket in the interval notation for this particular version of the range. And then, slightly different situation. if you analyze again any of the y values of the coordinates that make the dots that make up this curve here, they have a ceiling, all right? They have a maximum. You'd basically be running down, all right? You have to kind of think one-dimensionally, even in spite of the fact that it's a two-dimensional picture, just in this orientation, just in this orientation, whereas you're working in this orientation for the x's, all right? The interval, to summarize what y's are allowed, basically the range in this case, right, would be really going from negative infinity up to the maximum, and that's it. So it would be the y coordinate of the vertex, and it would include that, so you put a bracket. Let me split this over just a wee bit. Again, if you're looking for maximum and minimums, right, using your calculator, right, these are the options, right? If you hit second and then trace to engage the calc feature, you can have the calculator locate a minimum and maximum, which means that would be an x comma y value, all right? But you have to kind of know up front, well, would it be a minimum or a maximum, right, to begin with, just judging by the picture, all right? Again, it's either blooming or it's wilting, all right? All right. All right, that's it for today, all right? I'm going to look at the section 5.1 practice, and then I'll, assign that, okay? Thank you guys for sticking with me. I will see you on Thursday. All right, be careful out there.